Okay, good morning, student. So let us start with the class. Uh, we are in the third chapter, that is mathematical foundations. So within which we are learning how, whenever we are having the data, how we can go for performing the analysis, how we can come with the results, how we can come with the conclusion. And for this purpose, we are studying mathematical foundations in this chapter. So here, first we studied about the linear algebra, within which we have seen vectors and matrices. The next we started with the statistics, where we can describe whole data in terms of single set of data, in terms of lowest value, maximum value, average value. It means there are various ways to show the statistics. Then we studied about the correlation. In the correlation, that is, if I'm having two attributes, how these are correlated. If the changing in one value also changes the value of the another, then it means that that is a correlation. Then we studied about Simpson's paradox. That is, in group, if I come with the conclusion, so that conclusion may get reversed or disappeared whenever we are going for the subgrouping. The next, the subgrouping, it means that we are adding much more criteria. Initially, we have done analysis based on the two criteria or two dimensions. And later on, we added a third parameter or third criteria or third dimension or fourth dimension or another feature. Then results may get reversed. And for this purpose, and that phenomenon is called as the Simpson's paradox. The next, correlation and causalities we have seen. So causalities, it means that a sum cause makes an effect. That is, if I'm saying that X leads to Y, it means that because of X is the cause of Y. Because of X, Y existence is there. So the next, we started with the probability. So within the probability, we have seen the concept of dependence and independence. That is, if I'm talking about the events, so probability, it means that the event might occur. That is given by the probability concept. So within that, we have seen the dependence and independence. Dependency, it means that one event may give information about the another event. So that is called as a dependence. Whereas independence, it means that one event may not give at all any information about the second event or another event. Then in that case, we can say that the events are independent. Event, it means that something might occur. That is, if that is guessed that what is a probability or what is a possibility that this event or this might happen. Okay. The next, conditional probability we have seen, then Bayes theorem we have seen, random variables, continuous distributions we started with. So any doubt in the previous content? So I'm hoping to complete today this chapter. So actually here, okay, actually this content should be in this way. Actually, the central limit and theorem. Central limit theorem is part of probability and the hypothesis and inference. Okay, so this is within the hypothesis and inference, we are having the remaining 4 to 5 points. So, okay, clear with this? So now let us start with the today, that is continuous distribution. Let us see. So continuous distribution, it means that here we are having, that is between 0 and 1. When it comes to the previous values, that is whenever we are talking about random variables, where we are talking about the complete number, or that is occurrence of an event. For example, if we are tossing coin for the multiple times, then random variables, it means that for each of the event, if head occurs, I will assign the weight like 1. If tail occur, I will say this, that is 0. It means that here random variable will give me the idea that what can be the possibility within the 10 consecutive expressions, etc. Whereas when it comes to the continuous distribution, we are talking about the range of the values, that is between 0 and 1. I'm having multiple values which are continuously located. For example, in between 0, that is in terms of continuous distributions, we are talking about the real numbers. Real numbers where a fractional numbers we are talking between 0 and 1. I can divide it into 1,000 intervals, or I can divide it into lakhs, or 10,000, etc. Or I may divide it into 10 as well. So continuous distribution means that we are taking that complete each and every possible point within 0 and 1. Not only 0 and 1, it means whatever the range we are taking. So that whatever our graphs or whatever conclusions we are drawing, so within that, when it comes to the plotting, we always go for the continuous graphs. Just like here, I'm having random values. So Bayes theorem. So within that, we have seen that is whenever we are talking about the independent event, that is independent event, it means that because of E, if F is going to occur, and whenever E is not there, what is the probability of F? So on this basis, the Bayes theorem is there. So here, continuous distribution, it means that the uniform distribution puts equal weight on all the numbers between 0 and 1. So whatever continuous distribution is there, that is given in terms of multiple functions, just like probability density function. That is density, it means that how much population we are having. Population data set. Okay. So again, we have seen the plot. Again, we started with the normal distribution. So within the normal distribution, here, when it comes to the that is uniform distribution, that is continuous density function, then normal distribution, this is giving me a bell-shaped distribution that is completely determined for the two parameters, that is mean and standard deviation. The mean indicates where the bell is centered. That is, whenever we are talking about the bell, we are talking about the parabolic curve. So within the parabolic curve, where my bell is centered, and then standard deviation gives me how much wide that bell can be, or how much wide that uh, graph can be, or distribution can be. So here, this is the formula which is used. And later on, we have seen the implementation of this formula. So whatever these functions are there, that is 1 by root of 2 pi, then sigma, then expression, then to the exponential x minus mu square, then divided by 2 sigma square. So this complete mathematical function is implemented here. And then we plotted this graph. Okay, so here, based on the different values of standard deviation and mean, so these are the different graphs which are shown. So normal distribution, it means that this is giving me how much wide my graph can be, or my bell shaped curve can be, and what is the center of that. Okay, so here we can see the different values in different ways the graph is shown. So then here, whatever normal distribution is there, again within that multiple types are there, that is standard, normal distribution. When we can say that, that is a standard. So when mu, that is mean, equal to 0 and standard deviation is equal to 1, it is called as a standard normal distribution. If z is a standard normal random variable, then it turns out that is x equal to sigma z plus mu. Okay, so here this it means that this is my standard normal variable, and when it is also normal, but with the mean mu and standard deviation sigma. So then we can calculate that z equal to x minus mu divided by sigma. So that is a standard normal variable. Okay, and for this, it means for implementing these functions, we can go for defining the methods. Then, so this can be the this is a that is a for it means different values of sigma and mu. We are having these functions. That is when I'm having sigma 1 between range to between minus 50 to 50. So then sigma 1, sigma 2, sigma 5.0, and then sigma 1. So here different values are passed, and based on that the graph is drawn. Okay, so here when it comes to the standard normal deviation, so this in this way my graph can be. So then again inverse can be there. So sometimes we may need to invert this continuous distributions. Then in that case, we can reverse the values. So now let us go to the next point, that is the central limit theorem. So a central limit theorem, it means that here we are talking about, that is a normal distribution. Uh, that is right now, previously we have seen the concept like normal distribution, continuous distribution, and previously the probability, random variables, etc. So another approach is by using a central limit theorem. So here, one reason that the normal distribution is so useful is that because of the central limit theorem, which says that a random variable defined as average of large number of independent and identically distributed random variables is itself approximately normally distributed. So central limit theorem says that when we are talking about the data values, so within that, if I'm having independent event, that is I'm having number of large data sets and identically distributed random variables. Identically distributed, it means that just like 0 to 1, 1 to 2, etc. It means identically. So if in between 0 to 1, if I'm taking 50, then between 1 to 2 also I will take 50. But mostly we are taking the range as 0 to 1 only. So here, if this we are considering that, then it means that we are implementing the central limit theorem. In particular, if we are having x1, x2, x1, xn are random variables with mean mu, the standard deviation is sigma. Then if n is large, then we are taking summation of, that is mean, by using this function. So, and is approximately normally distributed with mean mu and standard deviation sigma divided by root of n. Okay, so here what if this function is there, so you might have studied about the addition of continuous numbers. Okay, so this is the same. For example, if I'm having 10 elements, okay, let me go to the slides. Okay, consider that I'm having 1 to 10. In between, I'm having 10 elements. So my n equal to 10 will be there. So then, if I wanted to perform addition of these values between 1 to 10, 1, that is 1 divided by 10. And in bracket, addition of all these values. I wanted to calculate the summation, average value. So 1 plus 2 plus up to 10, 10. So this will be equal to, this will be equal to 55 divided by 10 will be there, and it will be equal to 5.5 will be there. Okay, so this will be my standard mean. Sorry, this will be my mean and this will be my standard deviation. So previous formula, this will be mean, that is addition of n numbers divided by number of elements. And here, this will be my standard deviation. So equally, it means if actually this should be, formula is completely not written. Okay. So here equivalency, that is usually we use the, that is more formalized, much more formalized for normal distribution. Whenever we are having mean with mean 0 and standard deviation 1, so this formula can be used. So an easy way to illustrate this by looking at the binomial random variables. Binomial in terms of 0 and 1, which have two parameters n and p. Okay, so binomial NP random variable is simply the sum of n independent Bernoulli's random variables, each of which equals 1 with probability p and 0 with probability 1 minus p. So here, let me tell you about Bernoulli's random variable. So this is again between 0 and 1 will be there. Is any of the student is having any problem, doubts? So in terms of binomial, random variables is simply sum of n independent Bernoulli's random variables, each of which equals 1 with probability p and 0 with probability 1 minus p. So here, this trial we can perform by using this code. So I will, then the mean of Bernoulli's variables is p, then its standard deviation will be root of p in bracket 1 minus p. Okay, the probability of having that number is p for 1. And the central limit says that as n gets large, a binomial NP variable, approximately a normal random variable with mean mu equal to np and standard deviation sigma equal to n square root np in bracket 1 minus p. So for this purpose, it means this is my standard deviation. Sorry, this is my mean in terms of binomial theorem. And this will be the sigma value, that is in square root of np in bracket 1 minus p. So if we plot both of these, so this will be the function, that is we wanted to draw the histogram for that. So this will be the histogram when we are drawing this. So for example, if we call the 0 0.75, 100 and 1000, we get a graph like this figure. So this function, so this is using a bar chart type. So for binomial types. So first value is p, that is what is probability, n the number of elements, and the num points. That is, I will have the 1000 when it comes to this. So this is probability. These are the 100 numbers, and these are the number of points. So number of points between this to this curve complete, that is 1000, 10,000. These many points will be there, and n there are 100 numbers are there. So histogram we wanted to check. So data, we will apply the binomial theorem for uh, sigma in range n num points. So we show the bar chart. So for histogram, we plot this x minus 0.4 for x in x in histogram keys. So keys, it means that I will have the x value and this will be my y value. So num points, then we divide by num points for v in histogram values. Then we wanted to save the color as 0.575. So this actually color is given to this complete line. Then we can compute the mu p divided by n. P multiplied, that is mu we are calculating it as a np. So multiplication of these two. Then we wanted to calculate the sigma, that is standard deviation. So math square root, we wanted to take square root of this np in bracket 1 minus p. So this is my mean formula and this is my standard deviation formula. So we implemented this, and then we wanted to draw this, use a line chart to show the normal approximations. So xs range, that is minimum data and maximum data plus 1, and ys, then we call normal continuous density function I plus 0.5 mu sigma, and then uh, normal continuous density function, then applying plotting mu and sigma. And then by using the for loop, we can draw this by that is we can plot x's and y's. and then this will be the title assigned. So take a look at this functions and then I will show you the graph. So this will be the binomial distribution versus normal approximation. Again, take a look at this. So after this, we will start with the next point, that is hypothesis and inference. Okay, now let us go for the next point now. Hypothesis and inference. So within that, we are going to learn about 4 points, that is statistical hypothesis testing, confidence intervals, p-hacking, and Bayesian inference. So can anybody tell me what is meant by hypothesis? Or what is meant by inference? Okay, so hypothesis, it means that is we are making some conclusions. Uh, Sorry, hypothesis, it means that we are making some guess that this might happen. Okay, so hypothesis, it means that consider that previously in the 10, 11, if I'm having the profit of this much, and in 10, 12, I'm having profit of this much, and similarly consecutive 5 years, I check the profit that is for any of the enterprise. Then in 16, if I make a guess that if I'm having the profit in the previous consecutive years, consider I'm having profit like 20%, 21%, 22%, etc. Then on this basis, if I make a guess that in 2000, that is after 5 years of sales, in the 2015, if I make guess that in 2016, I will have the profit that is 26%. It means that that is a guess based on the previous values. And inference, it means that this is some kind of conclusion that is based on the reasoning, the previous values or evidence. On this basis, if we are making some conclusion, that is called as the inference. So this is my guess and this is my conclusion based on some previous values. So the science part of data science frequently involves forming and testing hypotheses. So about our data and processes that generate it. So it means that forming hypothesis, it means that I made a guess and then we tested. Tested, it means that in this year I make this hypothesis. I check whether this will occur. If so, then again in the next case I will make some guess. So it means that testing, it means that whether I'm achieving the existing or guessed value or not. Okay. So here, uh, that is whatever our process generates that hypothesis. That is our data. Our data generates or makes this hypothesis. Okay. So let us go for what is meant by a statistical hypothesis testing. So often we want to test whether a certain hypothesis likely be true. For example, that is whenever I'm tossing the coin, that is hypothesis assertions like head will be there, tail will be there, or then next. So consider that I designed some web page, etc. So within that I had added 4 to 5 links. Then out of 4 to 5 links, I may guess that for the first 2 links, student may or people may go for that link, but for remaining 2 are there, people will not go for that. Yes, in some cases, my guess may not be true, but here I'm making some hypothesis. So here it means we are making some guess, that is whether this will be true or not. So people are more likely to navigate away from the page without ever reading the content. If we pop up an irritating uh, interstitial advertisement with tiny, hard to find close button, etc., it means uh, if I'm giving some continuous pop-ups, etc., in that case, people will not go for the. So then here it means that this hypothesis we are giving based on some previous experience or some individual choice, etc., or previous experience. So here that if I'm teaching and continuously some pop-up is there or some message is there or random any noise is there, then it is likely to be that we may not concentrate on the lecture. So it means that that conclusion, that is, if this is happening, then this might happen. Or if this is happening, then this might happen. So that hypothesis we can perform. That is here, we are testing whether this hypothesis can be true. So under various assumptions, those statistics can be thought of as an observation of random variables from known distributions, which allows us to make statements about how likely those assumptions are hold or assumptions to be hold. So it means that whatever assumptions we are making, how many times we will get that true. It means this assumption will hold. It means that that is happening or that is making some sense. Or yes, whatever I have guessed, that is actually happening. So that is a statistical hypothesis testing. So for this, consider that in classical setup, we have null hypothesis H0 that represents some default position and some alternative hypothesis H1. Then we would like to compare it with, we use statistics to decide whether we can reject S0 as false or not. Okay, so null hypothesis, it means that I'm not making any guess. And in H1, that is here, if I'm making some hypothesis and here we are having some another alternative, just like this might happen, this may not happen. So in such cases, we will compare this and we will use statistics whether we decide whatever the hypothesis compared or we are guessing into H0 will that will likely happen or not. Okay, so that is a statistical hypothesis testing. Next is confidence intervals. So okay, you might be thinking confidence interval, confidence belong to a human behavior. Yes, here also we are talking. So whatever the points we are learning into this point, that is hypothesis and inference, that is this completely based on some assumptions. Okay, assumptions, that is this might happen. So confidence, Yes, with the confidence, I can say that something might happen. Then confidence, it means that on the previous basis, if as a person, if I make some guess, then how much confidence I'm having, that is given by this variable. So, but when it comes to the data science, we are talking about confidence intervals. So that is how we can deal with this, or confidence again given by, that is how likely that event can occur. So hypothesis is done on basis of probability, that is previous contents whatever we have seen. So another approach is by using a confidence interval around the observed values of a parameter. Okay, so here we are talking about the values, the existing value set, and based on that we will create an interval that within this time or within this range I'm having maximum values of the parameter. For example, we can estimate probability of unfair coin by looking at the average value of Bernoulli's variables corresponding to each flip. That is 1 if it head and 0 if tails. If we observe, that is 525 heads out of 1000 flips, then we may estimate that P equals to 0.2, 5 to 5. Okay, so here it means that we are talking about that this P, that is probability that this many times my uh, head might occur. So how the confident can be, we can estimate confidence. Then if we know that exact value of the P, the central limit theorem tells us that the average of those Bernoulli's variables should be approximately normal with mean P and standard deviation. Okay, so here we are having this formula, that is math square root. So you might be thinking, whatever the guess we are giving, so always whatever guess we are talking, please always we are talking in terms of some mathematical relation. Okay, so math square root P of, that is if I'm having the 1000 flips, then square root of P divided by, sorry, P multiplied by 1 minus P. The previous one, whatever we have studied here, yes, here, as per the Bernoulli's, whatever the standard deviation is there, this we are talking about. So then here we don't know the P value. Okay, so instead we use our estimate, that is whatever P right now we are taking. So that P we will take, that is 525 divided by 1000. So whatever this probability P we have taken, the same will be my mu, that is same will be my mean, that average of all those values. Then sigma, again we calculated this value, that is how much probability we are having. So P hat, this variable is used for showing the probability. Then P hat multiplied by 1 minus P hat divided by 1000. So this will show us that this will be the value. So this doesn't completely justify us. So people seem to be do it anyway. So using the normal approximation, we conclude that we are 95% confidence that the following interval contains the true parameters P. So I have come to this point. So here, when it comes to the normal two-sided bounds, so 95% confidence, it means that 0.95 mu and sigma. So this values we will pass. So in particular, we do not conclude that coin is unfair since 0.5 falls within our confidence intervals. If instead we would see 5 to 40 heads, then we would have, that is same different values, that is 95% confidence is there. Then we might have the two different values for this, that is normal side. So here you might be thinking, for which purpose these values are there? Actually, these values are calculated based on the normal distribution. So what are the formulas we are talking about previous cases? Here, here the normal, that is x we are passing, mu is 0 and sigma equal to 1. So mu and sigma, these two values we are passing. Similarly, we are calling this function here. That is previous, whatever the formulas are there, we are calling that. So within that, three values we are passing, and then we will get this values. two standard values and again. So this it means that between this intervals, I can have the 95% confidence. So here, fair point doesn't lie in confidence intervals. The fair point hypothesis doesn't pass a test that you would expect it to pass 95% of the time if it were true. So here we come with the conclusions. Okay, so these two are my normal size, that is 0.591 and 0.57 uh, 0.5709. Now this value, whatever sigma values we are talking, so that value doesn't fall within this range. So it means that whatever 95 confidence is there, that we cannot achieve. If this value is lies within this minimum and maximum values, that is confidence interval, then here we can say that the test is passed. If we are not passing the test, that is this value doesn't lie within this range, it means that the test is not passed, and hence we can say that a hypothesis does not pass a test that we expect to pass with the 95% confidence level. Okay, so next point is regarding p hacking. So p hacking, a procedure that erroneously reject the null hypothesis only 5% of the time, will be by definition 5% of the time erroneously reject the null hypothesis. Okay, so it means that p hacking, it means that that is a procedure where I wanted to reject the null hypothesis by 5%. Okay, null hypothesis, it means that we are making a set of some hypothesis, that is H0 and another H1 will be there. H1, the exactly reverse forward. And we may take the test whether H0 will pass or H1 will pass. Okay. So for this, we can run the experiments. So this is a code for that. So within that, for experiment consider, I have given for the 100 times. That is true equal to head and false. If it is false, then tails will be there. So here random variable will generate all the values. Okay, randomly generates value which are less than 0.5. Okay, so here for range in 1000. So for 1000 times this random variable will generate value which is less than 0.5. Okay, then this will return that value as an array. Then next, reject fairness. So within that, by using the 5% significant levels, we wanted to reject the hypothesis. So here, num heads I wanted to check. So length equal to flip for flip in the experiment if flip. Okay. So flip, we are saying it is true. That is head is there and false, tails is there. Now we wanted to calculate for the heads. So this will check whether in experiments, that is the previous code, if flip, it means that flip is true. That is whatever random variables we have generated. For this purpose, we are checking whether flip is there, true or not. Then next, returns num heads if it is less than 469. That is in between this range we are calculating. Then, so here random sets, so we passed 0. Then run experiment, we call the function for this calculating the values, and then num rejections we check whether length experiments for it. So we will check how much rejection will be there. So then we printed the num rejections. So what this means is that if you are setting out the significant really, then we usually can. So test enough hypotheses against our data sets, and one of them will almost certainly appear significant. Significant means that we achieve the test. It remove the right outliers. Right outliers, it means that within the data sets, we should identify which can be outlier. Then we can have the probability below 0.05. So this sometimes is called as a p hacking. It's some way a consequence of inference from p-values framework. Okay, I'm dealing with the p-values, that's why p-hacking is there. And inference, it means that we are making conclusion. So if you want to have the good science, that is excellent in case of guessing, then we should determine our hypothesis before looking at data. Then we should clean the data without hypothesis in the mind, and then we should keep in mind that p-values are not substitute for the common sense. That is, here we should not apply the common sense, we should apply the p-values only. Okay, so this is regarding the p-hacking. Take a look at this for a minute, then we will start with the next point. Okay, let us go for the next point. That is basic inference. Inference, it means that here we are not only making guess, so we are applying some reasoning as well. So this is another way to check the variables or check or make some conclusions, etc. So alternative approach to inference involves treating the unknown parameters themselves as a random variables. Okay, so in the Bayesian inference, we are taking whatever the random variables are there, wherever unknown parameters are there, we will take this as a random value. So analyst starts with the prior distribution for the parameters and then uses the observed data and Bayes theorem. So Bayes theorem, that is whatever prior distribution is there, and then we observe the data and then we apply the Bayes theorem. So Bayes theorem, just like probability of, just like we taken the example of which read about the Bayes theorem, that is if I'm having two tests, within the two tests, if consider at first test 60% students are passed, in the second test consider that 70% students passed, but between test 1 and test 2 common students passed are only 40%. Then here we are making Bayesian theorem, that is we are calculating that how many pass, how many will pass the both test, that we are checking based on the that is sorry, how many will pass the second test, that we are making conclusion how many students who have out of how many students who passed the first test also passed the second test. And another attribute we are considering here that how many students are there who had not passed the first test but passed the second test as well. Okay, it means that here these two conditions we are checking, and that is a base table. So we are applying here prior distribution, observing the data to get updated posterior distributions for the parameters. Okay, so posteriors, it means that after that, that is what conclusions we are making. So rather than making probability judgments about the test, you can make probability judgments about the parameters themselves. Okay, so here we are going for the parameter value checking or judgments. So for example, when an unknown parameter is probability, as in the fair coin, we are taking the example. So we often use prior from the beta distribution, which puts all the probabilities between 0 to 1. Okay, so here beta distribution, it means that all the probabilities between will be 0 to 1. So here, then a normalizing constant so that total probability is 1. So this will perform the calculations based on this formula. So beta and alpha. These two probabilities are there. So this will perform the gamma multiplication of these two and will return. So this is regarding the Bayesian inference. So we're not looking for this formula. So right now we are making here the Bayesian inference. It means that we are making guess for the parameter values, not for the actual conclusions. So actual conclusions, initially we are taking some random values. Random values, that is this might be 0.1 or this might be 0.9. So here based on these values, we are making some judgment. And at this point, I can give you the definition, that is Bayesian inference, where we are making probability judgment based on the test, that is test results. Instead of that, we perform judgment on the parameters values. So take a look at this and let us revise what we studied into the complete chapters. This was the last point. So, okay, so let us revise what we studied into the complete chapter. So today we studied about the central limit theorem, and we also studied the hypothesis and inference. And within the hypothesis and inference, we studied about statistical hypothesis, then uh, confidence intervals, p hacking, and Bayesian inference. So in statistical hypothesis testing, we are making H0 and H1 hypothesis, that is guesses about H0 and H1, and then we are checking how much of these tests can be done positive or can hold, or how much of these assumptions can be hold. So that is a statistical hypothesis testing. In the confidence interval, we are checking for the sigma and mu values, and within that we are passing the confidence intervals. So if consider our values lies between the confidence intervals, then we can say that it passed the test. If not, then that doesn't pass the test. Then in p hacking, so on the basis of p values, that is probability values, we are performing some hypothesis. And in case of Bayesian inference, we are making guess for the random values. Okay, instead of going for the test, whether test will conclude or not. In Bayesian inference, we are using observed data. We are using observed data and Bayes theorem, and on this basis we are making how this p value is changed, and p value is nothing but a probability values, and that we are checking or using as a random variables if the unknown value is, sorry, any unknown value we are replacing with the random values, and then we are checking how it will lead to the test. So here, all the points from the third chapter are over. So I will conclude that this chapter is over. So in the next lecture, we will start with the chapter 4. And before that, tomorrow you might need to appear for the class test for the chapter 2 as well as chapter 3. Okay. So if consider time allows, then I'm thinking for the lecture only. But see, well, let us see what will happen. So in this week, anytime a test can be there. So be prepared. If you're having a doubt, you can ask. Please don't leave the meet. Let me take the attendance. Okay. So I will stop the recording now.